Hello, so today we are talking about inference for means. So think about means, that's the mu and x bar symbols we're going to be working with today. This is section 9.3 in your textbook. Please go there to follow along and see extra practice problems. So let's start with what we've been talking about for a long time now. We have a significance test. And in a significance test, there are 4 steps, and they're the same steps every single time. If you already have these in your notes, you do not have to rewrite them. We've written them a lot so far this unit. But just to recap, state, population, parameter, and my 2 hypotheses. Plan, random, normal, independent. Today, normal is going to be normal for means, not for proportions, and we'll talk about how to determine if something is normal for means. Step 3 is the do step. That is my substitution into the formula and to calculate the p-value. And step 4 is conclude, where we have my conclusion, reject or fail to reject, connection to the p-value, and context where I reference my problem. So today we said we're doing a test about means. So when I think about substitution into the formula, I need a new formula for means because my formula for proportions isn't it. So this is a one mean t-test. This is the test statistic, or we also call it the critical value. For a one mean t-test. So this is the title of today's test, a one mean t-test. I use a one mean t-test when I don't know sigma, but I'm using the S, or the standard deviation of my sample, to estimate sigma. So the big kind of difference now is that I have a new formula, and the formula is dealing with t, because t is what I use when I know S, but not sigma. And this goes all the way back to confidence intervals. So think about this formula. It's saying the critical value, or t, equals the sample mean, or my sample or statistic, minus the population mean, or my claim, divided by the standard deviation of the sample, which we've seen a lot this year as S over the square root of n. So we've seen all these pieces before. Now we're putting them into this puzzle to find my test statistic, or my critical value. So key point number 1 is the larger your critical value, the more extreme your sample is. If I get a critical value way up here, that's a really extreme sample. That's a really extreme x bar. And the more extreme my value is, the smaller this probability of getting it is. However, if I have maybe a bigger critical value, if my critical value is closer to 0, then I have all this area, or this really big probability of getting that value. So the larger my critical value, the more extreme, and the more extreme, the further I am over here, or I should also show, the further I am down here, the smaller my p-value is going to be. So if I have a large critical value that's extreme, or very far from 0, the center, the smaller my p-value, which means the more likely I will be able to reject my null hypothesis. So we're looking for critical values that are more extreme because those are going to help me reject my null hypothesis. But sometimes we're going to get critical values that are close to 0, and those are not as extreme, and you'll see they have a higher chance of happening, meaning it's not an extreme or rare observation. So this is a conceptual key point. It's talking about the further I get from 0, the smaller the chance is that I could see that sample just by chance. So let's look at an example and kind of go through my 4-step process with this example. So it says sweet corn of a certain variety is known to produce individual ears of corn with a mean weight of 8 ounces, So the mean of all of the ears of corn is mu, which is 8. But a farmer is testing new fertilizer designed to produce larger ears of corn. So we're thinking they're going to be bigger ears of corn now, as measured by their weight. He finds that a random sample, or 32 randomly selected ears, so randomly selected ears of 32, N is 32, of corn grow with this fertilizer have a mean weight of 8.23, so the sample mean weight of those 32 ears of corn is 8.3 or 23 ounces with a standard deviation of 0.8. So the sample standard deviation is 0.8. So I wrote out my knowns, and I want to know, do these samples provide convincing evidence at the alpha equals 0.05 level that the fertilizer had a positive impact on the weight of the ears of corn? Justify your answer. So justify your answer and provide convincing evidence should tell me I need to do a significance test. So let's start with the state step and do my population, parameter, and hypotheses. So the population comes from the WHO. Well, I took a sample of ears of corn, so the population is all ears of corn. Technically, it's all ears of corn of this certain sweet corn variety, but if you say all ears of corn, I know and the AP reader knows that you know what you're talking about. The parameter, or what we're measuring, is we're measuring their mean weight, or the average weight of these ears of corn. So we want to test a claim about the average weight of corn. So I'm testing a claim about the average. What told me average was this mean weight, and then it's talking about the average weight or the mean weight. For my hypotheses, I still have the null hypothesis. Well, the null hypothesis is always equals. Since the problem is talking about means, I know it's mu equals. Well, what was the weight of the population for the ears of corn? Well, it tells me that they're known to have a weight of 8 ounces, so the null hypothesis is that mu equals 8. The alternative is what I think is going on, and I think that they have a mean weight greater than 8, and I think that this fertilizer is producing larger ears of corn, so the alternative is that mu is greater than 8. So this is the state step. I can then go on to the plan step. First part of plan is random. Well, it says randomly selected ears of corn, so it's stated that it's random. Check. For normal, I can't do the NP and n times 1 minus p greater than or equal to 10. It's normal, and the problem's talking about means. So since it's a means problem, what rule can I use? Think about it. If I have a sample of 32, what rule tells me for means that it's a normal sampling distribution? The central limit theorem. N is greater than or equal to 30, so I can use the CLT. So for means, it's normal if my sample is greater than or equal to 30, or it's stated in the problem. So sometimes it would be stated that it's normal. Lastly, independent. I can assume that the population of ears of corn is greater than or equal to 10 times 32, or I can assume that all the ears of corn, there's more than 320 ears of corn. So that's an assumption we're making, and we can also assume that each ear of corn is separate or independent from the next ear of corn. Well, then we get to the do step. So we did state plan. Now we're at the do step. And let me just write out the knowns that we wrote on the first slide. So we said that X bar was my sample weight of 8.23 and the sample standard deviation was 0.8. We know that the claimed mean is 8 ounces and I have a sample of 32. So we already identified these on the first slide. Well, if I think about doing a one mean t-test, I know it's a t-test because it gives me the standard deviation of my sample. When I go to plug in my data, I get t equals my sample, or x, minus the mean divided by the standard deviation of 0.8 over the square root of n, which is 32. Well, once I get to this step, I can do the arithmetic in my calculator. If I think about the top of 8.23 minus 8, I get 0.23 for the numerator. And for the denominator, I get 0.1414, or just 0.141. When I do that division, I get a t equals 1.6312. If I rounded 4 decimal places. If you round 3, that's okay. So I get that my t, or my critical value, equals 1.6312. Well, usually I use the t value, or the z, to then go to my table to find the area. But can I use t on my z-score table? No. I have to use my t-star table. So key point number 2 is for a one mean t-test. I use the t-star table to find which two p-values my critical value is in between. So we're going to break this down in a minute, get all this information down, just the key point, don't copy down the table. Get this key point down, and then we are going to apply it to this problem. So let's take a look at this table. If I think about my table and what I know that t equals 1.6312, and I know that my sample size is 32. Well, if we think back to how do I determine which one of those degrees of freedom I use, we said degrees of freedom equals n minus 1, so 32 minus 1 would give me 31 degrees of freedom. Is 31 on my table? Nope, so I'm going to go down to 30. There we go. I'm just highlighting it so we know which row we're looking at because it helps me. So if I think about being in the row of 30, because I have 30 degrees of freedom, I want to find where is my t value in this row. So I kind of look through my row and I say, where do I get to my t value? Well, if I think about it, my t value would be right in between here. 1.63 is in between 1.31 and 1.697, or sorry, 697, which means my p-value is going to be in between 0.05 and 0.10, or in between 5% and 10%. So when I go to write my answer, t equals 1.6312, I know that my p-value, is going to be in between or less than 0.10 but greater than 0.05. Or my p-value is going to be in between 5% and 10%. So this is how I estimate my p-value. If I'm using my table, I cannot find the exact p-value. I just know my p-value is going to be in between 5% and 10%. However, I can use my calculator to find the p-value. But if I use my calculator, no matter what, I have to show my substitution into that formula, meaning I have to show t equals 8.23 minus 8 over 0.8 divided by the square root of 32. I have to show this substitution in order to use my calculator and get full credit. But if I was going to use my calculator, here are the calculator steps. So we are going to go through these together in class, but just so you can follow along, you go to Stat, then Tests, and then instead of number 5, you're going to go to number 2, which is a t-test. You're going to highlight stats, not data. So if you want to follow along on your calculator, now you can. Then you're going to type in the mu naught, or the claim from the null hypothesis. In this case, it would be 8. Your x bar would be 8.23. Your standard deviation is 0.8. Your sample size is 32. And you want the greater than mu naught alternative hypothesis for this example. Well, then if you press calculate, or you can press draw, you are going to get a very nice looking normal curve. And you're going to have t over here at 1.6263 is going to be the more official value it gives you. Remember, your calculator is way more exact than we are with our rounding. And then this p-value it gives you up here is 0.057. And this 0.057 is the p-value, and that was in line with thinking that my p-value was in between 5% and 10%. It's in between those two at 5.7% or 0.057. So if I think about my p-value, I got my p-value to equal 0.057. Or if you used your table, you knew that your p-value was less than 0.10 but greater than 0.05. So no matter which method you used, if you compare your p-value to alpha, the p-value is greater than alpha, and you can say 0.057 is greater than 0.05. So since p is greater than alpha, we can fail to reject the null hypothesis claim that the true average weight of ears of corn is equal to 8 ounces. So the steps are the same and this template's the same. It's just now we're talking about the average weight instead of the proportion. So remember, we can find our p-value two ways. One is with the calculator. This is the more exact method. Or you can use your table and see where does your t-value line up with your table columns. Based on these p-values, we would draw the same conclusion that it's greater than alpha, and we fail to reject. So that's a wrap. For a one-mean t-test, we know the sample mean and sample standard deviation, so we know x bar and sx. We use the calculator or the t-star table to find the p-value. The calculator gives me the exact one, the table gives me the range. And that is section 9.3. See you next time.